the opportunity to speak here. It's dangerous to invite an academic to an applied conference like this. The introductions today were great. I want to try to build on this theme of snow and what happens to snow, and how basic research that's being performed by universities in Utah, really around the Western US, can help inform water resource management in a time of change. The photo on the left here is actually a snow survey when we were doing ground truthing for LiDAR mapping. That's my class, taking snow cuts, snow density, and structure measurements. And then the picture on the right is our water resources coming from snow that we've talked about. I thought that there were only two people talking. And so I'm going to go through this really quickly, or as quickly as I possibly can, and give you a rapid fire story of emerging knowledge, emerging information about how water moves through our landscapes, from snow into soil, into ground, and eventually into streams and reservoirs. Things that we think that can be useful for predicting in the future in a time of change. So Stephanie early on talked about the change. We have climate change there on the top left. We have population change. Those are constraining our options for water availability and water management. We have drought as the new normal. We're either in drought or preparing for drought, as Candace Hassenegger likes to say. And then we have widespread landscape changes. And so the conditions in which we've developed forecast models have changed tremendously. We want to try to take information from individual research studies that point to a common new understanding. So they're not just one-off studies, but new understanding, and figure out how we can take all that nuance and all that geeky information that an academic scientist might focus on and put it into something that's useful for prediction. And so we can look at the Weber as a case study. We have a number of studies in the Weber River watershed that we've been looking at for about the past 6 or 8 years or so. We can look at the long-term history of stream flow, and that's the Plain City gauge where we look at, and we see tremendous interannual variability in stream flow there. We see a decline in discharge from 1908 to late 1930s, and that's really when much of the water infrastructure that Darren was talking about was built out. We're largely built out from that time. And then more recently, over the last 20 years, we're seeing more and more consecutive dry years or low flow years. If we look at the water use within there, this is the hardening of the water use. We're moving from agriculture to municipal, industrial, and Weber. If you think of the watersheds of the Great Salt Lake, the Jordan is almost all gone to municipal and industrial. Weber's intermediate, and the Bear is still much more agriculture. Those are conditions on which we need to respond. It's a hardening of water resources. It's a lot harder to control water going to someone's tap than it is to an agricultural field. So the question is, how can we improve prediction in a time of rapid change? What is the information that all the geeky scientists running around in academia can help to inform decision making? And we published a paper a few years ago that tried to summarize this. We looked at hundreds of studies, and we really put it down to what Scott just talked about, how much precipitation there is, how much snow there is. That's our driver. That's our primary water source. How does it melt, and then where does it go? And what I want to talk about primarily here, or focus on here, is where does it go part. We've learned a lot about how snow melts and infiltrates soils and makes it to the thing. And the take-home message is most of it goes in the ground. So we're going to go to the whole Great Salt Lake watershed here, look at a retrospective analysis. We have absolutely amazing data. We have better data here on climate and stream flow than anywhere in the world. It's a fantastic place to identify new relationships and new processes. And it's also not a bad place. Every now and then I get away from my computer and get to go out and take some measurements, that photo on the left. So we have a long-term climate record. We have a lot of diversity. And if we move up into the headwaters, we see the same type of interannual variability in precipitation and stream flow. But we don't see that human component anymore. We don't see that decline from 1908 to 1930. We just see that interannual variability. If you look at stream flow down on the bottom, you see some longer periods of low flow, even up in the headwaters. So this is telling us something about how climate may be changing, how drought, how warming temperatures may be influencing what we're seeing. But it's a nightmare for people who are trying to predict what's coming through, whether it's CBRFC, the SNOTEL survey, anyone, it's a nightmare. And this is an example just from Great Salt Lake watersheds. The numbers on the left are the variability in runoff efficiency. So that's our best estimate of stream flow at gauges divided by our best estimate of precipitation. 9 to 59% of the precipitation that falls, depending on the catchment in the year. The figure on the right is a scatter plot. How well does the amount of snow we get each winter predict stream flow? It's highly, highly variable. We saw that in 21, 22, and 23, where we had stream flow that wasn't quite what we expected, given the snowpack that we had in the mountains. And so one of the hints on why that's occurring comes from chemistry. And so since last century, since I was a graduate student, we've had chemical data that suggests that the chemistry of the stream never looks like the chemistry of the snow. It always looks like the chemistry of the ground. That's what this particular figure is meant to show here. Specific conductivity is the figure on the lower right, is just how much charge can be carried by the water. And that only comes from having lots of things dissolved in the water. Fresh snow has a specific conductivity of 20. We're looking at specific conductivities of 400 or 500. It tells us that the water's been in the ground, and it's probably been into the ground for a while. So just like soil moisture is a metric of how wet the catchment is, and Darren mentioned that in the first talk this session, groundwater, or the amount of water coming out in our streams in the middle of winter when precipitation is accumulating in the snowpack and not going into the stream, is a great metric of how wet the catchment as a whole is, not just soil moisture, but groundwater storage. And we can measure that in the figure of the left in the middle of winter. We focus on the size of the peak because that's the water that we manage. If we go back in the winter, there's tremendous variability in the winter. The figure on the right shows that variability in the winter in every catchment in the region, and this is true now in much of the Colorado River Basin, follows this periodic pattern. And so that says that there's a climate driver that's influencing water in storage. If we look at that, we can see that the amount of water in storage, in groundwater storage, it's not just a function of what happened that year or during the fall, the rains in October. That's certainly part of it. But it's really how much precipitation, how fast it melted for the previous 4 or 5 years, and how warm the previous 4 or 5 years are. So if you take that information on how much groundwater is in storage and you plot it over runoff efficiency, they match beautifully. Now we have a situation where the chemistry says that the water's been in the ground, and the runoff efficiency, or Q over P, tracks wonderfully with how much water is in the ground. We're starting to think we have a good predictor for how much water we may have coming out each year to better inform water management. A simple example of doing this is starting with stream flow right about now, in the middle of January or February. What's the level of stream flow right now? We use that as a coefficient, the same way anyone who's worked with a Snow 17 model or snowmelt runoff, simply a coefficient multiplied by the amount of precipitation we get results in that figure on the right. Far less uncertainty in predicting the amount of water that we have. So if you go through here and if you now track precipitation and stream flow, the stream flow is remembering or reflecting not just the snow that fell that year, but previous years. If you look at the time period to, I don't have a mouse that's working very well here. So if you go from the late 1980s, you can see a series of dry years. Relatively low precipitation years. And you see it slowly start to increase until you get to the late 1990s, but you really don't see a response in stream flow, even though you're getting a little bit more precipitation. Those are examples of stream flow remembering the low groundwater storage from the previous years. The bad news is, so the good news is that we can do a better job of predicting runoff efficiency, which means we can do a better job of when you spill water from the reservoirs. If you're working in any reservoir throughout the rest, actually, we can do a better job of thinking about how much water may be available for agricultural interests so they can better plan what they might want to plant. Having a better idea before the Colorado River Forecast Basin Forecast Center updates their prediction through spring and early summer. We have the ability to provide an advance warning. Is it more likely to be wet or more likely to be dry given the amount of precipitation we have? Bad news is that these increasing temperatures are decreasing groundwater storage, and so we're seeing continually lower runoff efficiencies. The question is, why does this work? Quite often, I'll presented to the river forecast centers before. In 2 weeks, we're presenting to the Upper Colorado River Commission or the Hydrology Working Group. It's very different way to look at how water moves through the mountains. We tend to think that snow melts and runs off very, very quickly. And so this data suggests, these observations suggest that water is really in the catchment for a long period of time. That means it may be used by plants or may contribute to groundwater or stream water somewhat later. We can assess that with tritium. So tritium is the water molecule itself. It's radioactive. It decays with about a 12.3 half-life. So if we know the tritium content in a snowflake, and we look at the tritium or the snowpack, and we look at the tritium content in the stream flow, we can determine how long it took that water to come out, how long that water's been there. And if we look around the western U.S., from California to Colorado and New Mexico up through Wyoming, the age of groundwater, the age of water in the middle of winter, is 14 years in sedimentary or clastic high permeability catchments and 6.5 years. In the Weber Basin, we've dated the water in the Weber Basin. It's about 13.5 years old on average. That's how old the winter stream flow is. So what does that matter for stream flow predictability? We don't have gauges everywhere. We don't have information everywhere, but we know the geology everywhere. And we know that the age of water varies with geology, and runoff efficiency is inversely related to the age of water. The longer it takes a water molecule to exit a catchment, the more likely it is to be lost as evapotranspiration to go back to the sky, the less likely it is to contribute to downstream flow. Next. So this is a interesting point. How you would think that, okay, I'm trying to boogie. So you would think that stream flow still, even if groundwater is 13 or 14 years old, stream flow during snowmelt's probably going to be pretty young, right? We would think it's that snowmelt that's running off the surface. Throughout the western U.S., it takes about almost 6 years for an average molecule, an average snowflake water molecule to exit a stream flow. In the Weber Basin, it's 4.1 years. It's a little bit younger. And again, it varies based on geology. So we clearly know that these catchments are not acting as a pan with a little sponge on top of soil. They're acting as a bucket. And how full that bucket is, if there's low storage, you're going to get low stream flow. If there's high storage, we're going to get higher relative stream flow for the amount of precip that's in the catchment. So that's really, really quick overview of how we're taking information from chemistry and isotopic tracers on the fundamentals of how water moves through the catchment and coming up with simple metrics. How much groundwater storage that helps us inform prediction in the future. It takes years for us to refill our groundwater. And so the take-home message is, here's hoping for a whole string of years like 2023, so we can fill up groundwater, and then irrespective of how much snow we have coming in the future, we'll have relatively high runoff efficiencies from that higher storage. All right, that was whirlwind tour. All right, that's it. There's got to be questions. That's 27 years and probably 50 people working on those projects, summarized in 14 minutes and 37 seconds.
You did an amazing job getting through that, and so clearly, so thank you. I'm curious about the connection, just because we were hearing recently, the one bit of good news is that we have high soil moisture at the moment, and any connections between that and ultimately groundwater storage.
So that's a tough question. So we've been looking at soil moisture since I was young and had hair. And it helps. It certainly helps. It's used in all our forecasts. We only have soil moisture in a few locations, and just like we saw in snowtail sites. And as Tom Painter is actually a colleague of mine from grad school days, the end of the last century, right? We only have observations of soil moisture in a few locations. And so we have had historically more trouble relating soil moisture to runoff efficiency than we have groundwater, which is an integrated metric. And so it's another way to measure antecedent wetness, but it integrates all the variability through the catchment rather than the individual places where we have measurements. Hopefully that kind of answers your question. Sometimes soil moisture works really well, but a lot of times it doesn't.
So are there other isotopes you use to measure the age of that water, or is it just the tritium? Because I know there's others.
So there are other ones, but
Because it seems old.
it's
The runoff, I wouldn't have guessed that.
It does seem old. Most people wouldn't guess it, and most people go, no, it can't be. I presented chemical equilibrium models and strontium isotope relationships, which clock how long water's been in the ground as well. Those are less intuitive because they involve chemical reaction kinetics. Tritium is the only one that works for water that's exposed to the atmosphere. So once it's down below the water table surface, we can use other noble gases, we can use other tracers of age. But because those equilibrate between the air and the water, tritium is the one that we can use. This particular study that I showed data from the ages from California to Colorado and New Mexico to Wyoming, because there was a general thought that water really can't be that old, I don't know what that's going to tell us. It took 5 years to get that study funded. But the story was consistent across all of those individual catchments, from the Sierras to the Front Range of Colorado to Snake River out by Jackson and down in the Rio Grande in New Mexico. So while we don't have another age tracer unique to the water molecule itself, tritium is the water molecule.
So yeah, thanks for the presentation. So are we saying when a snowflake falls today, if we had snowfall today, assuming we did, when that flake, falls and hits on, the watershed up in the mountains, before my wells pump that water, on the Wasatch Front, the connectivity as far as age there, are we saying that's about, what are we saying the time is between when that snowflake hits the mountain and I pump that water out of the Wasatch Front? Can you venture a guess on that? Are you saying that's 14 years for the Weber Basin area?
No, this is only for the headwaters. So this is right up in the small headwater catchments where 14 years. As you get down into the basin where the wells are located, the water gets progressively older. So this average of each of these numbers are an average of. There's some water that makes it really, really quickly, like we might envision. And there's some water that is extremely old. There's some recent work looking at wells near and adjacent to the Great Salt Lake, all the way out onto the front, that is suggesting some of that water might be 10,000 years old. So that's looking at really, really old flow paths. Those are going much deeper and much longer. Some wells, if they're deep enough, may access some of that water. But this is primarily looking at the year-to-year variability of what's coming out of the mountains. And now we know it's not a year-to-year variability. It's about 5 to 7 year variability. It tends to be reproducible. There are other, in those wells, there are other H tracers work that do. Some of the noble gases will work really well to give you an idea of both what elevation that water recharged and how old it is as well. There are other ways to get at that.
Okay, thank you.
Maybe one more?
Come on, I don't want to keep you from lunch, but.
Yes, I was wondering, it seems like your model is mostly associated with kind of natural recharge up in the mountains, but in urban areas and other developed areas in the mountains or other human activity, would that actually increase the runoff efficiency, or do you see any evidence for that?
So you're right. Most of our work has been up in the mountains. That's where our snow water resources primarily originate. We've done a little bit of work lower down at the mountain front and into urban areas. We see broadly similar patterns. And surprisingly, we see even in urban areas like the East Bench of Salt Lake City, in those areas, we see surprisingly old water and larger fraction of water infiltrating and going into the ground than simply running off the surface. And as we trace that water, it's very time consuming and expensive to try to get little packets of the water. See, is water may run off a parking lot, but then when it gets into a natural surface, it will go into natural or historical swales and channels and then infiltrate in those channels. So there might be a short-term surface runoff, but unless it's completely paved pipe and managed into a stream or conveyance, larger conveyance, it's quite likely to recharge. So we can see signs of water recharging on the University of Utah campus coming out in the stream in the fancy neighborhoods just downstream from campus. So they don't like that. They're not happy about that. But that general rule that most water seems to infiltrate tends to hold, at least when we get into campus type areas and residential areas.
Okay, thank you.